If you're generating an unstructured mesh, you may have noticed that your mesh generator offers many different options for how you can fill the volume of your CFD domain. Some options which you may have include tetrahedral, polyhedral, or hexcore approaches. In this talk, I'm going to be looking specifically at the hexcore approach. I'm going to be showing you the idea behind the hexcore approach and why it's a good idea for some applications. I'm also going to be showing you some of the controls that the CFD mesh generator may give you access to that you can use to control how your hexcore mesh is generated. And I'm also going to be looking at some subtleties in the differences between different types of hexcore meshing approaches. So if you're using a hexcore approach or you've used one before and you'd like to learn some of the background behind it, this is definitely the talk for you. All right, let's get into the video. The first idea that we need in order to understand hexcore meshes is to understand that the ideal cell for the finite volume method is a perfect cube. So a regular cube with no skewness, all sides the same length, a perfect cube is the ideal cell for the finite volume method. Why is that? Well, it's not actually the cube itself that makes it ideal, but it's when the ideal perfect cube is connected to other identical perfect cubes of the same size. That's the key here. When those perfect cubes are connected to each other, then if you imagine drawing a line or a vector between the centroid of one cube to the centroid of any of its neighbor cubes, that vector is orthogonal or at 90 degrees to the face that's shared between the cells. And the reason that's important, it comes up in the mathematics of the finite volume method, but simply what you need to understand is that when that vector is orthogonal to the face, we don't need a non-orthogonal correction. And I've done videos on the non-orthogonal correction, you can look that up, but what you'll find is that if you're using ideal perfect cubes that are all connected to each other, you don't need a non-orthogonal correction. And in simple terms, that will mean that the convergence of the algorithm that you're using in the finite volume method, whether that be simple or piezo, the convergence will be improved because the non-orthogonal corrector acts as a source term and slows down convergence. So that's the ideal cell, a perfect cube connected to other perfect cubes of the same size. Now we could use the same reasoning and deduce that perfect cuboids, so think of this as that perfect cube but just stretched out one of its axes. Perfect cuboids also have orthogonal faces. The only difference here between a perfect cuboid and a perfect cube is that a perfect cuboid has an aspect ratio that's greater than 1. And again, we would still get that same orthogonality benefit using perfect cuboids. And the additional benefit with a perfect cuboid, of course, is that if we know the direction of the flow and we know the direction of the gradients, so for example, very close to the wall in a boundary layer flow, we know that the gradients normal to the wall are much steeper than they are along the wall, then a cuboid can be a more efficient way of filling the space because we can have lots of fine cuboids normal to the wall but stretch them out along the wall, and so we would have less cells in our mesh and we would more efficiently fill the space. So cuboids are similar to perfect cubes, but the reason that we want to actually use perfect cubes and the motivation for a hexcore mesh is actually away from the wall. So we're not thinking about close to the wall, we're thinking about away from the wall when we think about hexcore meshes. And generally, when we're away from the wall, we actually don't know what the flow direction might be. And of course, if you're near the inlet of your geometry, you may know the direction that the flow is coming, and so cuboids might be fine for that particular area. But in general, for a general geometry, when you're away from the wall, the flow could be going in any direction and you may have strong gradients in any particular direction. And for this reason, the ideal mesh away from the wall is perfect cubes that are regular and of the same size, because that means regardless of what direction the flow is and what direction the gradients is, we'll be able to get equal resolution in the solution and also have that benefit of not requiring a non-orthogonal correction. And the reason we don't want cuboids away from the wall, of course, is because they may be oriented in the wrong direction, particularly if we don't know what direction the flow is in. And that can lead to issues with the current number and aspect ratio, which I've been through in a previous video. So you can always go back and look at that video if you want some more information about why you wouldn't want to use cuboids away from the wall, even if they are perfect cuboids. So we've got this idea that away from the wall, the ideal mesh to have in a CFD domain would be perfect cubes of the same size. And of course, we could alternatively use polyhedral cells away from the wall. That would provide a similar effect, especially if they're regular sort of polyhedral cells. We'd be able to capture that resolution and gradients in different directions. But I don't really want to focus on polyhedral cells in this talk. I only want to think about Hexcore meshes and the motivation for them. So the idea still stands that away from the wall we want to use perfect cubes that are all the same size and connected to each other, so we don't have that non-orthogonal correction. But we also have to remember when we're building a mesh that we want to minimize the total number of cells in the mesh so that we can reduce the simulation time of our CFD simulation. And to do this, what we would like to do is to use small cubes closer to the wall where the gradients are high. So after we come away from those inflation layers and from the boundary layer, our cubes, we'd like them to be quite small, but then further away from the wall, perhaps in the free stream where nothing much is happening, the gradients are very low, and we don't need high resolution, we could use larger cubes, and that would be a more efficient way of filling the space. We wouldn't want to take those small cubes and fill the entire domain, because that wouldn't be an efficient way, and our mesh would be too big. So this is what we want, but of course this leads us to a problem. Remember that the condition was that ideal cubes are only best for the finite volume method if they're all identical and have the same size. But that leaves us with a problem. How would we transition between the sizes if we can't change size? And this brings us to the idea of the Hexcore transition and how we transition between perfect cubes in a Hexcore mesh. And many of you who've seen Hexcore meshes and used them before know where this is going, but hopefully now you can see the motivation for where the Hexcore approach comes from. And the trick and the key to the Hexcore transition is every time we change the size of the cubes, we want to double the dimensions of the cubes each time we change size. That's the key aspect for the Hexcore mesh. And for those of you who've done a lot of meshing before, another way to think of this is that you're setting the growth ratio to 2. So every time you change cell, you're going to be doubling the size of the cell in that direction normal to the wall. And this, of course, is different to what you may have used before for a typical tetrahedral or polyhedral mesh where the growth ratio may be a lot lower, and you're probably more used to seeing growth ratios of 1.1, 1.2 or 1.3. In the Hexcore approach, you want to think of this as a growth ratio of 2. And the reason this works is that when we set the growth ratio to exactly 2, it means that when the cube dimensions are doubled, we can connect them together directly without changing the shape of the cubes. And you can see this here in this simple example. I've got some smaller cubes here with dimension x, and of course when we stack 4 of them together, we can connect them to a larger cube on top that has dimensions 2x by 2x. And you can see there's been no change to the shape there when we've done that transition. And of course, using this approach, it doesn't just have to be in one direction. We could connect those perfect cubes along any of the axes of the cubes. And all the time, we're maintaining those perfect cubes which have the same shape. And another important part of this Hexcore transition is to actually notice what's really happening here when it comes to the types of cells we're using. Now, originally we were using perfect cubes, and using the nomenclature of meshing, a perfect cube or a perfect cuboid is often referred to as a hexahedra or a hexahedral cell because it has 6 faces. That's where the hex prefix comes from. But of course, when we connect those cubes together, what we've actually done is we've imprinted the faces of those 4 small cubes on the bottom of the hexahedra. And if we count the number of faces, we've actually got an additional 3 faces there on the bottom. So even though our cell is the same shape, it has additional faces. Each of these segments of that bottom face count as different faces. And of course, if we did the same, if we connected 2 sides of that larger cube, we'd now have 12 faces. And what this means is that this transition cell between the small cubes and the larger cubes is actually a polyhedral cell. It has many faces. And it's important to notice the distinction here that a polyhedral cell is actually based on the number of faces and not the shape of the cell. So it's not that distinctive kind of bubbly shape of cell that defines something as a polyhedra, it's the number of faces. So actually what we've done here is we've introduced a polyhedral cell which just has a very regular shape. And this is why you'll sometimes see this meshing approach referred to as a poly-hexcore, because one of the features of the hexcore is that the transition between cells is a polyhedral cell. Now, unfortunately, this method of transitioning between small cells and large cells isn't without a cost. If you think again about that vector that connects the cell centroids across the face in the finite volume method, of course, when you have only small cubes, that vector is orthogonal to the face, it's at 90 degrees, and so are all of the other cells. And the same when we only have the large cells, that vector is orthogonal to the face. But when we're transitioning from the small cell to the larger cell, if you draw a line representing that vector, you can see it's not intersecting the face at 90 degrees. And so there's a small amount of non-orthogonality that's introduced in the transition between the small cell and the larger cell. And so the non-orthogonal correction will appear in both the smaller cell for this face and also the larger cell for that face as well. And typically, as you can even see just from the diagram here, that actually the orthogonality angle is still relatively modest. This small amount of non-orthogonality isn't going to cause any problems for the stability of the solver. We haven't introduced a severe amount of non-orthogonality. This is just an imperfection, you can think of it that way, in the setup of our mesh. So we haven't quite got that ideal mesh anymore of perfect cubes everywhere. We've just got a slight imperfection in the transition region. And for this reason, this is why you may notice that some mesh generators that use this polyhedral transition actually distort the faces of that transition cell there, pitching them down. And so now you can see that if you draw the same line from the centroid of the smaller cell to the larger cell, it's now closer or may even be equal to 90 degrees. And in this case, the non-orthogonal correction would disappear. So you may sometimes see this if you actually look very closely at the polyhedral mesh. Some mesh generators will be distorting the angle of that transition there. But ultimately, for us as CFD users, this is hardly going to affect the quality of the mesh and the quality of our results either. So it's not something to think about in too much detail. Now, the Hexcore approach that we've been through so far has quite an important limitation to it. And what I want you to do is imagine that you have some mesh with a wall here, and there are a few inflation layers being grown off the wall. And then after those inflation layers, we're using a Hexcore approach, as we've described, where we start with small cubes, perfect cubes of equal dimension, and they're connected to a larger cube by using that polyhedral transition, and then that cube itself is connected to a larger cube, and then we've reached the free stream mesh size. So each time we're doubling the dimensions of those cubes. And the problem with this approach, you can see if we just sketch an example of how a velocity or temperature profile might look normal to the wall, we can see that through the inflation layers we're getting a lot of resolution in there, we've got a lot of cells, and so our linear approximation that we use in the finite volume method is well able to capture that profile normal to the wall. But of course, as we move away from the wall, their gradients are still present. Even though we're not in that very thin layer of inflation layers right at the wall, there are still gradients in the flow solution. And you can see that when you transition from this small cell to the larger cell, there's a sharp jump in the profile. And so we're actually getting quite poor resolution of the solution there. So the transition is too rapid. A growth ratio of 2, even though we've used it to maintain those ideal cubes, a growth ratio of 2 is far too rapid. What can we do about this? Well, it's actually pretty easy. What we can do is we can actually add an extra layer of cells in this Hexcore progression before we transition to the next size. So you can see in the diagram here, I've just added an extra layer of hexahedral cells before we go to the medium cell. And then for the medium cell, again, I've added another layer of medium cells before we transition to the larger cells. And these extra layers of cells are called buffer layers. And when we do that, just sketching the same profile that we had before, you can see that we're getting a lot better resolution slightly off the wall. And this is actually giving us a really good match for the profile. And we don't just have to use one buffer layer, of course. We could use 2, 3, 4, or several buffer layers. Each time we're just adding an additional layer of cells before we transition to the larger cell. So this diagram on the left, we've got one buffer layer, that's one extra layer, you can think of it that way. And in this diagram on the right, we've got 2 buffer layers, so 2 extra layers before transitioning to the larger cells. And so buffer layers are great because they're improving the resolution of the solution close to the wall, but of course you may notice that we're of course increasing the number of cells in the mesh here because we need a lot more smaller cells than we do larger cells. So clearly there's a compromise here. We want a compromise where we have the right level of resolution that we need for an accurate solution, but we don't want too many cells. And this is the reason why many mesh generators, when you come to apply a Hexcore approach, you'll see the default values in the box may already be filled in with 2 or 3 buffer layers. So the CFD mesh generator will probably be going for an approach that's something like this, or maybe even more buffer layers, and that's why. But what is it about 2 or 3? How has that number been arrived at? Well, actually, if you just take a simple unit square like this and you apply 2 buffer layers, for example, then you see that we have the small cell here, we have 2 extra layers, 2 buffer layers, before we double the size of the cell. And you can just do this simply, graphically plotting, and you can see that roughly this is how the size of the cells increases as we go away from the wall. And if you compare that to a regular geometric growth ratio of 1.2, which is what you might be used to, you can just see visually comparing the two that we're getting a similar progression of cell sizes away from the wall, even though with the Hexcore approach, of course, we're having to wait a few layers before we jump up and double the cell size. And this is exactly why something in the region of 2 or 3 buffer layers are often recommended as a default by the mesh generator, because we're getting a similar effective growth ratio to if we had a growth ratio of around 1.2. And it's really important to remember that with this Hexcore approach, even though we're adding buffer layers and reducing the effective growth ratio down from 2, which is just pure doubling, down to something which is similar to say 1.2, there is still the abrupt change in the cell size. And so what that means is that if you plot your solution normal to the wall, there will be some jumps in the solution resolution each time you go up a level of cell size. And you may see this if your jumps are particularly sharp as a discontinuity or a sharp change in your contour plots or line plots. And so for this reason, particularly when you're using a Hexcore approach or any other, you should always really be looking at the solution and checking visually, are you getting the level of resolution that you need? And there aren't any noticeable sharp changes in the solution. And of course, if there are with the Hexcore approach, you can either add buffer layers or reduce the size of the cells. Those are some ways to get around those sharp changes. Now, I want to draw your attention to an alternative method of transitioning between the small cells and the larger cells, because this is used by some Hexcore mesh generators, and you may have seen this before. And the alternative transition, the reason for this alternative transition is that some CFD codes want to use a Hexcore approach because those cube-shaped cells are ideal and we would like to use them if possible. But some older CFD codes, for example ANSYS CFX, can't actually use polyhedral cells. Polyhedral cells are more of a modern innovation, And so it means if we want to use a Hexcore approach with those types of codes, we need some kind of method of transitioning between the smaller cubes and the larger cubes without that polyhedral cell. And I've just drawn a sketch on the slide here to show you visually how you can do a transition without a polyhedral cell. The way to understand this is, imagine you have 9 small cubes and you'd like to transition to a larger cube that has dimensions that are double the size of the smaller cubes. What you want to do is align that larger cube with the central cube from the block of 9. And what you're going to do is create a hexahedral cell that connects that small central cell out to the edges of the larger cell. You can see that hexahedra in there. This is a skewed hexahedra, it's not a regular hexahedra, but it does connect those faces together without using a polyhedral cell. The next thing to do is insert pyramids onto those corner cells of the 9 smaller cells on the bottom, and then finally we can fill in the gaps with prism cells. And you can see that that does a great job of allowing us to transform from those smaller cubes out to the larger cubes in the Hexcore. And of course, these transition cells, the prisms, the pyramids, and the hexahedra in the middle, don't have as high a quality, and they will have small non-orthogonal correctors. But if you've ever seen this approach before and looked at meshes, you may have noticed that often that pyramid has the same dimensions, or roughly the same dimensions as the smaller cube, and clearly that's a very high quality pyramid in there. The same with the prisms and the hexahedra in there. The cells aren't perfect, but they do have high quality, and so it means ultimately that the non-orthogonal corrector that's introduced between the faces is going to be small between those cells and isn't going to give a large effect on the solution. And because this method of transitioning between layers in the Hexcore doesn't use polyhedral cells, sometimes you'll see this just referred to as Hexcore without the poly prefix, and sometimes you may see it referred to as hexa-interior or other. But hopefully by now you've got a good understanding of what the differences are between the different types of Hexcore transition, and actually it's this method of transferring between smaller cubes and larger cubes that glues the whole Hexcore approach together. This is what we want. We want larger cubes away from the wall with no non-orthogonal correctors, and we want smaller cubes close to the wall for higher resolution, again with minimal non-orthogonal correctors and allowing us to resolve that solution. So have a look at your mesh. Can you spot the transition? Do you have a polyhedral transition, or do you have a non-polyhedral type transition between cells? Now, the final thing I wanted to talk about in this brief introduction to Hexcore Meshes is just the general approach that the mesh generator is going to use when you try and create a Hexcore mesh. And this is generally more useful for your understanding, and of course if you want more detail, often you should look in the user manuals, and that's where you'll find information for how your particular mesh generator works. Generally speaking, the Hexcore approach is a top-down meshing type approach. What does that mean? Well, if you take the example of airflow over a car or another vehicle, then your CFD domain will typically look like a box with your aerodynamic object in the center. And what the Hexcore approach will do is start by dividing the entire domain into the large cubes. So remember, in your Hexcore approach, you've got a hierarchy of sizes down from your largest cells all the way down to your smallest cubes. And the Hexcore approach is top down, so it starts by dividing the entire thing into cubes of the size that you specify. So as part of the controls for your Hexcore mesh, as well as specifying the number of buffer layers, you'll often have to specify a global mesh size, and this is where that size is coming in. It's going to set the size of your largest cubes. And a quick side point here, it's worth noting, and you may have spotted this before, that your Hexcore cubes are always going to be aligned with the global coordinate system, so X, Y, and Z, unless you've changed something in the controls of your mesh generator. And so what this means is that if your domain is at an angle, maybe you have a pipe inlet that's at an angle that's not aligned with your meshing axes, or in this example we're doing a car going downhill, then the cubes will be aligned with the XYZ coordinate system and not necessarily with the axes of your domain. So that's something to watch out for, and sometimes you can control and modify the orientation of the cubes in your Hexcore. And if you can't, one thing you can always do is mesh in a coordinate system where your car is aligned with the global axes, and then later, once you've done your mesh, you can rotate it using a meshing tool of some kind if you really want to get the orientation of those cubes in a particular direction. Once the mesh generator has done that, once it's divided the entire domain into those perfect cubes of the large size, what it will then do is the mesh generator will look for the cubes that intersect or are close to the boundaries. That's all boundaries. So the wall boundaries, the velocity inlets, the pressure outlets, the wall of the car, and anything else you have in your domain. And if the mesh generator identifies that the cubes intersect with the boundary or are close to it, it will subtract away and divide those cubes into smaller cells. And you can see this in my second diagram for you there. And of course, these cubes will be half the size in terms of all dimensions. So one large cube will be divided into 8 smaller cubes in 3D, but 4 in 2D. And once again, the process continues recursively. So again, the mesh generator will now look at the medium-sized cubes and delete and divide them into the smaller cubes again. And hopefully you can see from this recursive process that the mesh generator is going top down and continuing to divide those cubes and delete away to sculpt out a rough outline of the boundary. And this recursive process will go on until the size of the cubes is locally equal or similar to the surface mesh resolution. So that means if you have a small feature with a very fine mesh around it, locally the Hexcore will continue to divide until the smallest cubes are of similar size to those surface features, because ultimately that will mean an easier transition for the mesh between the surface mesh and the Hexcore. So for you, you can actually work this out before you even start pressing mesh. Think about what's the largest cube in your domain, how large do you want it, and then look at your surface features and think, how many times is that Hexcore going to have to divide until the smallest cells, the smallest cubes, well capture the layers and the transition cells close to the boundary. So that's a very useful exercise. And of course the final bit is when the Hexcore is finished dividing up and splitting all the cubes and deleting things out, inflation layers will be added around the surface of the body, and then somehow the mesh generator will transition from the layers out to the Hexcore. And this is partly why we want those cubes to be as close as possible to the size of the surface mesh. And I've been through this in my previous video on pyramids and stair stepping. You'll understand why it's important for those cells to have a similar size. And I don't want to go through too much in this talk about how the mesh generator transitions from the layers out to the Hexcore. I've talked about that briefly in another video, and ultimately it's not important. The important thing is your understanding of roughly how the mesh generator is building that Hexcore mesh. So let's quickly summarize what I've been through in this brief introduction to Hexcore meshes. The Hexcore mesh fills the volume of your CFD domain with perfect cubes that are all the same size. They're identical and they're the same size. And it's those features which make the cubes so desirable, because the cubes, when they're connected together, they don't need orthogonal corrections, which is ultimately going to improve the speed of convergence and the stability of the calculation. And they also provide equal resolution in all directions. So it doesn't matter which direction the flow is going in, the gradients will be equally well resolved regardless of where the solution ends up being. And this goal ultimately imposes a restriction on the Hexcore approach, which is how we transition between cubes of different sizes while maintaining the same shape. And the way we do that is by doubling the dimensions of the cube when we transition from a smaller cube to a larger cube. And of course, this constriction on doubling the cell sizes requires us to make an abrupt transition between the sizes, and that transition may be polyhedral, or it may be a mixture of pyramids and prisms. But ultimately for us as CFD users, we need to check the solution visually, either using contour plots or line plots, to check that those abrupt transitions in the cube sizes don't artificially affect the solution and give us poor resolution in certain areas. So that wraps up my introductory talk on Hexcore meshing. I'm really hoping with this talk that you've actually understood some of the theory and the background for Hexcore meshing and why such a type of mesh is desirable and why it might be used. I'm also hoping that you can now go back to the mesh that you're currently making and maybe have a look at the structure of what the mesh generator has produced, and maybe you'll get some insight on the various features of the Hexcore mesh and what type of transition is being used and why the cells are dividing where they are. And as always, if you found this talk useful, let me know in the comment section. I really do appreciate your comments and I really enjoy hearing from you. It does let me know that the videos I create are actually helping people out, and that really means a lot to me. And thank you all very much for watching and continuing to support the channel, and I'll see you in the next video.